such that you can see them in that first column that you see. Then I can go through and count those. Last time they were just in the rubric and not in the main one, which I can do either way. But yeah, so if it's in the rubric, you still have to like take that value and put it in the grade, or at least I didn't really figure out a way to do it on that. But I can do that by calculation.
Yeah, that sounds good.
Okay, let's get started. Yes, let's get started. How's everybody doing today?
Amazing.
Amazing. Awesome. That's what I like to hear. Exhausted. Existentially exhausted. That's different. Hopefully that gets better. Okay. All right, so announcements. Homework 2 is out. Did everybody see this on Canvas?
Yes.
And you got updates via email about it? Things like this. Okay, good. That is due 1 week from tonight at 11:59 p.m.
From 2.
Cool. Okay, so let's look at it real quick. Okay. So here it is. Basically, the first part is just the formulation of a constraint satisfaction problem. Right? So AI, these are very hard problems, generally NP hard or worse. And so oftentimes the trick is forming your problem in such a way that other people who have already devised really good ways of solving these problems with various heuristics of various efficacy, you can apply their solutions to your problem, right? Like frequently that's what modern AI boils down to when you're trying to solve problems and not doing research about problem solving. So what we have here is just some very simple scheduling problem, and then what we're asking you to do is just formulate that problem as a constraint satisfaction problem, such that you could then apply any constraint satisfaction problem solver to do it. Does that make sense? So we're not asking you to solve the scheduling problem, just to discuss, consider, and write down ways that you would formulate that problem. Does that make sense? Okay. That's part 1. Part 2 is this minimax tree here. So we did a couple examples like this in class, right? So the idea is you're going to perform a variety of searches on this, detailed by the questions here, and then also perform alpha beta pruning, right? Does that make sense? Okay, and so one question that's already come up is when we say, what is the path selected by minimax? Where did it go? There. Path. That is, for instance, if the node, the leaf node that produces the value up here is this one, the path would be this path down the tree. Does that make sense? That's what we mean by path. Cool? Yes?
So we would just, if you wanted us to list the edges, and then you mentioned alphabetical order, like we could just put like JRT in terms of an answer, or J comma R comma T, or did you want like
yeah, so the
specific format, I'm guessing.
Right, so well, the listing the edges in alphabetical order really is only when there's some ambiguity to the ordering. So like if you talk about what edges are pruned, that's just some set that's unordered, right? And so you could just list those in alphabetical order. This actually has some notion of ordering, right? So either way though, it's fine. Does that make sense? Cool. Okay, so that is homework 2. Do we from the day?
I have a question about the first problem.
Yes.
So the second part of the first problem where we're writing the constraints, like in the book there's multiple ways of writing constraints. We just choose like any of those formulas.
Yeah, just as long as it makes sense.
Okay.
And it's going to be depending on other choices that you make about kind of the domains. Yeah, just as long as it makes sense. Okay, other announcements. Project 1 grades are coming soon, as in tonight or tomorrow. Project 2 is coming soon, as in today, we hope. So that will be due prior to the end of spring break. It is roughly equivalent to Project 1 in complexity-ish. So, sound good? All right, so clarification from last time. We had this question about this notion of estimating probability distributions via samples that we were gathering kind of online. right? And so this was kind of the format that we've had. So if we're taking the expected value of some distribution, we have this explicit formula up here at the top. It's the sum over the outcomes, probability of the outcome times the outcome, right? And so that's the explicit formula. And then we had kind of approximated this with these two ways at the bottom here. So if we collected some set of samples here, then we can say in a model-based way, we're going to explicitly approximate these probabilities based on what we've seen, and then we're going to compute this approximate expected value based on that estimation of the probabilities, right? And then we also said, well, there's this other way to do it. You can instead take a model-free approach, which is where we kind of ignore this explicit representation of the probabilities and just do this average over the samples. And the question came up, does this make any assumptions about your distribution, or how does this even work? Because you're just averaging over some set of numbers. How does that actually come out to an expected value of some arbitrarily complex probability distribution function, right? And so I thought that really quick, we could go over an example to kind of clarify that point. So I've left these equations up here at the top. This is the true value. This is our model-based estimation. This is our model-free estimation, right? So let's say that we have two possible outcomes, and their values are 1 and 2. And it's not uniformly distributed, so we can say that the probability of 1 is, for instance, 0.75, and the probability of 2 is 0.25, right? So we can take the true expected value of this, right, which is times, right, plus 0.25 times 2, which is what, 1.5? Right, so here's our true expected value because we know the probabilities in advance. But now we say we don't know the probabilities, right? We instead want to estimate this expected value based on sampling, right? So let's say that we sample from this distribution, and what we end up with, we'll do it 10 times, is something that looks like this, right? This is our sequence that we got from sampling. These are our outcomes in order, right? We did it 10 times. Okay, so if we look at the model-based approach, what we're going to say is we're going to look at this, right? We're going to explicitly estimate these probabilities, right? So we have p hat here of 1. That's going to be the number of times we saw 1, which is 1, 2, 3, 4, 5, 6, 7, over the total number of samples, right? Does that make sense? Okay. Similarly, we can take the estimated probability of 2 occurring, right? And what we get is the number of times that happened, which is 3, over the total number. Okay, so this is explicitly estimating this, and then we can take our model-based expected value, right, and say that that's the sum of these estimates times the outcomes. Right, so we get 0.7 times 1 plus 0.3 times 2, which is 1.3. Right? So it's not exactly the expected value that we would get from the true distribution if we knew it in advance, but that's because we're sampling, right? But if we took enough samples, we would converge to that value.
Well, it's actually closer. I think that's 1.25.
Yeah.
Is it 1.25?
Yeah.
0.6, right? 0.6 plus 0.7.
No, on the true expected value.
Oh, did I say 1.5? 1.25.
Yeah.
Okay, sure. Algebra mistakes aside. Okay. Online algebra is not my strong suit. All right. So this is then the estimate that we get from this model-based approach, right? But if we instead take the model-free approach, then what does it ask us to do? This is this equation up here, right? It asks us to take a sum normalized of this sequence here, right? And that adds up to 13, right? Okay, so this value here is this value here. And that's because these two things are mathematically equivalent. Okay, so the true intuition here that I want you to get is that because we're getting these values from the distribution, that distribution is already being accounted for in some way, right? We're drawing samples from the distribution that we don't know, and using that to estimate what we know. So that's what we're doing in these online update methods like Q-Learning. Okay, but you'll notice it's making no assumptions at all about what the distribution looks like under the hood, right? Because we're sampling from it, it's influencing what we're learning. Make sense? sense? Yes.
But it seems like the sample space that they would guess things happening from is not even the same, because in this example, in the start, if you know the probability of 1 is 0.75, the probability of 2 is 0.25, you know that it's going to be one of those two things. So when you're making guesses, you're only going to guess one of those two things. But when you're pulling from the distribution, you don't know sort of what the possible set of answers is.
So these are discrete.
Yeah. So you might guess something that is not even within it. Even if it was sort of only whole numbers, you could still have like a 75% chance of a 20 and a 75% or a 25% chance of a 5. But then you would guess something in the middle every single time that is neither of those two real values.
Yeah, because we're estimating the expected value. We're not estimating some actual value that you get out of it. Right? This is our expected values we're kind of all through this probably. Right? It doesn't have to, the expected value doesn't have to come from your set of values. Does that make sense?
Yeah.
And so we're using the expected value to influence decisions about what we go next, right? We say we have some set of actions from some state. I expect the value here to be some number. I expect it to be some number here. I just pick the best one based on those expected values. That doesn't have to be an actual value that you can get, right?
I thought when we were guessing like the ages of people in this class, the goal was to like guess the next person.
Oh no, the goal is just to compute the expected value without knowing the distribution in advance. Yes?
So num A and n, is n the sample size?
N is the total number of samples.
And then num A
It's just the count of that.
how many samples we have of that action?
Yes. Of that outcome.
Of that outcome.
Okay. We feel better? Awesome. Okay. Other questions from last time? All right. Let's move on. More reinforcement learning. A review. Okay. So quickly, what we're doing is we still assume that we have this MVP, right? And so that consists of some set of states, some set of actions. These can depend on the states, right? And this model T, this is the transition probability, where it's the conditional probability to choose action S. You choose action S, or if you start in state S and choose action A, this is the conditional probability that you'll land in S prime. Right? That's T. We've seen this for a couple weeks now. And we also have this reward function, right, that happens when you make that transition to S prime. Okay, so we're still looking for this policy. The policy, again, to reiterate, is a way to choose actions given the state that you're currently in. Right? So it's some function or explicit representation of the action that you would want to choose given a specific state that you find yourself in. Right? Okay. And then the difference between regular MDPs and reinforcement learning is now we don't know those transition probabilities and we don't know the reward we're going to get from them. So we have to kind of try things out in the world, see what happens, and then reason over that. Okay, and so the big idea from last time is that we would start to compute averages over these transitions and what we saw when it happened using sample outcomes, right? Which we were just talking about a little bit. And so we're going to kind of build on those concepts in a big way today and on Thursday, but to kind of motivate why this would happen, I'm going to give you some examples of real-life uses of reinforcement learning that the methods we've covered so far wouldn't handle, or the methods we're going to cover today and next time will. So here's a helicopter. Has anybody flown a helicopter?
I mean, flown one or flown in one?
Yeah, flown one. Okay, I haven't either, but I've heard it's difficult. And the intuition there is that helicopters kind of, unlike airplanes, don't really want to fly, they want to fall, right? And so it requires kind of constant correction, I've been told, from helicopters. So here's reinforcement learning, the results of reinforcement learning flying a helicopter. We don't need that. Pretty impressive, right? Oh, wait. So that reinforcement learning agent is flying a helicopter, but not a second. Which is what it was supposed to do, to be clear. That's what they were trying to get to do. But just to kind of give you an idea of the kind of problems they could solve. So we saw similar problems like this. So we have this simulation of this kind of walking robot living in some physics simulator and starting to learn how to locomote effectively.
I guess the example goes up.
Here's it on a different kind of robot, the same
Oh,
method.
that's horrifying.
Here it's trying to learn how to stand up. That's how I stand up in the morning.
It's like normal yoga routine.
That happened when I turned 30. I don't know, it was a really stressful but it hurts a lot too. Anyway, so here's kind of some basic kind of motion actions that you can do that you can learn via reinforcement learning. Maybe it gets a little more complicated. What about playing soccer?
Gosh, I want to make this. Oh, scored.
Actually, this like twinkle toes prep kicking the ball is how my toddler kicks balls too. So the parallels just keep coming with the toddler. Kind of scary. Here's a real life task. So this robot's trying to learn how to manipulate, in a very restricted sense, some objects. So it's trying to put this peg, some shaped peg, in a shaped hole, right? It eventually figures it out.
Does it?
It does. All right. But I don't want to say it for a minute. Next time I'll see it. Here's one of NASA's robots that they're recently working on. But basically the idea here is that you have these rods that are connected by these cables, and you can kind of vary the length of these cables. And the idea here is that this would be able to roll over kind of arbitrarily complicated terrain on something like Mars or the moon or whatever. But how you actually move this system to get it to do things that you want, that's a very difficult question to answer. And so they're using reinforcement learning here to learn how to move this up. More real-life robotics manipulation, in-hand manipulation of this cube in order to achieve some goal pose based on the camera. This is also a long video, and my scrolling forward is not working great. But I'll post the videos online so you can see. It ends up learning how to do stuff effectively. Okay, so kind of relating what we've seen so far in reinforcement learning and MDPs more broadly, if we have this known MDP, where we know these transition probabilities, we know the rewards associated with them, we can solve these offline using the MDP methods that we've talked about, right, which are like value iteration, policy iteration. Fallacy iteration is the combination of those, I guess. If you have some fixed policy pi, you can do policy evaluation. That's one of the two components of policy iteration, right, where you're varying the policy, evaluating a suboptimal policy, right? And so we have these optimal values we're trying to compute, D star, Q star, pi star, right? I'll review. Okay, but then we don't know these transition probabilities of the rewards. That brings us into the reinforcement learning domain. And we had two kind of big categories for solving these, right? We talked about model-based, which we just went about, which is where we're kind of explicitly considering the MVP problem structure, right? We're estimating these transition probabilities and the rewards potentially, depending on the type you're doing. And then you're reasoning over those the same way you were reasoning over MVPs in the past, right? And then we're not going to talk too much about that in this class, but there's a lot of really, really exciting research happening in that kind of space. But we want to focus in this class more on the model-free version, which is where you're not going to explicitly represent those things in the MVP. Instead, you're going to construct concepts and algorithms that kind of rely implicitly on that concept. Okay, and so we talked about a couple different ways to do that last time. Direct evaluation, temporal difference methods, things like this. Right? Okay, so in model-free learning, the concept is that we're going to experience the world through these kind of episodic trajectories, right? We had some here in our diagram that we've seen so much. We start in some state, we just take some action or observe an action being taken. We land here, we see what happens, we look at the reward, we just go on and on, we just watch it happen, right? And we can either have some suboptimal policy that's driving this, or we can just observe it happening if another agent's doing it, and learn things about that as we go, right? And so we update these estimates each transition, and over time, these updates kind of mimic the Bellman updates that we saw when we were solving MVPs. So what we'd like to do in Q-Learning, which is kind of as far as we got in reinforcement learning, is we want to estimate or converge on the true values of these Q values, right? So the Q value, just to reiterate, is the value of being in state S and having chosen action A before you see what happens, right? So we're living in this stochastic world. We start in S, we choose A, we end up in S prime, right? But that ending up in S prime is actually sampling from some random distribution that we don't know, right? Okay, so that's what the Q values are, and we kind of looked at this. This is the Bellman updates relating Q values to previously seen Q values, right? So this describes some dynamic programming problem that you can solve. But we can't really do this update without explicitly knowing T and R, right? So the concept that we came up with last time is instead we're going to average these things as we go. So if we receive some sample transition, right, this gives us some sample, which is described here, and we want to average over the results. And so the intuition behind that, we kind of covered with that example earlier. Basically the idea is that we instead of explicitly modeling this distribution, just take samples from it, right, and learn as we go. And since the expected value is the thing we actually want, we can do so effectively. And so we wanted to keep this notion of a running average, right? And so we had here our old estimate, right? This is the result of our sample, right? We're still keeping around this table, Q values. This is how we update them, right? And so we weight this, what we used to know, by 1 minus alpha, where this alpha is this learning rate, and we weight what we figured out this time by alpha, right? And we update the value in our table, right? Okay, so one of the things that we talked about in like the last 30 seconds of class last time that we might have missed because we were backing up is an amazing result. And that's that Q-Learning converges to the optimal policy even if you're not using the optimal policy to do the learning. I'm going to give you a second to think it because it blew my mind at this time. So you can act suboptimally. You can just do random things under some restrictions or move in a suboptimal way in any kind of way you want under some restrictions. But at the end of the day, Q-Learning is going to provide for you something arbitrarily close to the real Q values, which will give you something arbitrarily close to the optimal policy. Okay, this is called off-policy learning. It's an important concept. The idea is that what you're learning is not specifically related to the policy that you're using to learn it. Yes?
So what's the difference between like what we witnessed earlier is like iterations, how many times it has to go through to learn these optimal paths versus simulating these iterations in computer time versus having to do it in real time?
So there's still this notion of iterations, right? We're still exploring the environment under some notion. We're still updating these estimated Q values. That's an iterative process. But you're kind of having to experience the world versus just reasoning offline. So they were all iterative methods, both for solving MDPs and for doing reinforcement learning. The difference that you're keying in on there at the end is that, and this is a key important difference, in MDPs you reason online, there's no simulation at all. You just do a bunch of math over the problem definition and come up with an optimal policy. In reinforcement learning, you have to experience the world, and that can either happen in simulation or in the real world. So if you're trying to learn something about some robot that's moving through the world, you can either physically place the robot in the world, right, and observe what happens when it tries different things, or you can have some notion of a simulation that is pretending to do that, right, which can happen much more quickly and is also generally much cheaper, because if you have a robot that's flopping around randomly, it's likely to break, right, and that can be very expensive. But it can take a lot of time too. You can imagine it's much faster, especially if you're not visualizing every run of the simulation. It can be much faster to simulate something rather than actually to have it work in the real world. Yes?
With actual robots, when they're learning doing, how stochastic are the actions that they take? Like the results of those actions? Is it generally pretty set or not?
So it depends. If what I'm trying to do is just move some rotational joint, generally that can be pretty deterministic. But if that joint is then interacting with the world in some way that I care about, then it can become stochastic, right? So there's some, if I'm trying to grab this water bottle with some robotic hand, where I move the fingers to, deterministic, roughly speaking. But whether or not it slips through my hands or slides instead of being gripped, that is determined by some physical effects that I don't have control or knowledge of. And so functionally that looks to me like a stochastic. Does that make sense? And so if what you care about is it doing something relatively complex involving the world, it can be very stochastic. Yes.
Can the robot combine both simulation and physical movement, so it can run through the simulation internally and then figure out the optimal movement and then just do it in one try?
Yes, absolutely. So you're describing something that the machine learning community, in a very broad sense, calls transfer learning, which more broadly means that you take experiences, you take some notion of having learned on experiences in one domain and transfer that knowledge to a different but related domain. And so in this instance, that looks like learning how to do something effectively in simulation and then transferring it to the real world, which the simulation is supposed to be modeling, right? And so that's a very good idea, and a lot of people do that. Yes?
Will we be going over some form of caching in terms of these iterations? Like, let's pretend that we have a robot that can simulate 100 times, and that robot after 100 simulations has learned X amount. Would transfer that information to perhaps a secondary robot with similar actions or deeds?
Yeah, so that would fall under the same umbrella of transfer learning, which is now you've got something that's related but slightly different. The idea is that you take what you learned there and apply it to a new problem, and then fine-tune what you've learned over here. Very good idea. Yes?
How do you apply methods like this to continuous state spaces? Like, it's not just like I'll move in 5 degree increments with my fingers, right? It's continuous.
Very good question. So there are extensions to all of these that work in continuous spaces, is one answer. Another answer is that frequently you can kind of pretend that you're living in a discrete space by kind of binning things or discretizing things into a grid, things like this. But you lose some notion of accurate modeling up to the resolution of that grid when you do so, right? And that can cause problems. So,
It can still be very expensive if you're doing development, right?
yeah, so how finely did you discretize something is going to probably be one of the dimensions in your state space, right? And so that's going to have huge implications for the size of your state space. Okay. Let's look at Q-Learning running. Okay. So this is that grid world that we looked at last time, where it's kind of exploring the space. Each of these triangles represents one of the Q values from that square, right? We're trying to learn the Q values. And so you see this agent that started out kind of moving randomly because it didn't have very much knowledge about where it should be, right? And which directions it should be moving. And now it's starting to learn more and more about which places are good and the policies associated with getting there.
Does this have the random movement option where you can pick a direction and can move?
Yes, so this does have some notion of exploration, which we'll talk about here in a minute. But so,
Can it accidentally slip from like 10% chance to 11%?
yeah, so there's some stochastic behavior associated with the action choices that's being accounted for. Similar to, it's being accounted for in the math in the same way that we've talked about with MVPs, but it's also being accounted for in the simulation. Okay, so as you kind of really hit on, there's this notion of exploration versus exploitation, right? When we saw that example a couple lectures ago of the slot machine, the one that always won $1 and the one that sometimes won $2, but we didn't know the distribution, we kind of had this idea that we would try out this red slot machine that sometimes gave us $2 and kind of get an idea of how good it was before we went back to the one that we were positive would give us $1 every time, right? That was exploring to learn, and then at some point we had to switch over to exploiting what we had learned in order to actually achieve some goal, right? And so there's this notion of how do you smartly choose when to explore, when to exploit, and how to do that over time. So the example here is that let's say that you have your usual favorite restaurant, it's really good, but a new restaurant opened up. You try the new restaurant, you're positive you like the other one. The new one may be better, but probably not, given how much you like the other one, right? So what do? That's this kind of general concept. So how do you decide when to explore or how to explore? There's several ways to do this. The first one we're going to talk about is this notion of epsilon greedy, which is this kind of concept of taking random actions. So every time step you flip some coin, and with some probability, usually small, epsilon in this case, we're going to call it epsilon, I mean, you act randomly. But then with 1 minus epsilon probability, you act on your policy. Right? So what are some of the problems we can have associated with this concept? Eventually you've learned all there is to know, but with epsilon probability, you're still going to be doing random things. Right? Does anybody have an idea about how we might mitigate this?
Perhaps start branching off after a specific amount of learning. So maybe begin this in the beginning of exploration, and then perhaps at the end implement a less explorative and more exploitative form of.
Yeah, so you could say, for instance, after some fixed number of iterations, you then just use what you've got, for instance. Right? Anybody have any other ideas? Somebody we haven't heard from yet today, how about you?
Would you have to decay epsilon and alpha separately?
So, decaying epsilon is a good idea here, and what I was hoping to get to. And then alpha is this different concept. You would want to decay them kind of both at the same time, but the rate of decay kind of depends on your problem and needs to be set as a parameter.
Yeah.
Did you have another idea, or was that your idea?
That was my exact.
It's a good idea. Cool. Your idea was good too. They're all good ideas. Okay, so yes, we lower epsilon over time, either in a discrete big one step or with some scheduling. Okay, so let's see how that might look. Okay, so you all remember this crawler, right? We have this 2D physics simulation where we've got this box. On this box are 2 links of some 2-dimensional robot arm, right? And so we can change the angle with respect to the box of this yellow joint, and we can change the angle with respect to the yellow joint of the red joint, right? So we have 2 degrees of freedom here, a 2-dimensional action space, and we're trying to learn how to make this thing crawl forward, right? So the idea here is that we have this high epsilon. So you can see it here, it's 0.8. And so 80% of the time we're going to do something random. So it's learning a lot of things about the space, but it's not really effectively moving around, right? But if we lower that epsilon, then we start to leverage the policy that we've learned. And the key takeaway here, if we watch this again, is that we're just a few iterations in, but here in a second we can skip 30,000 steps ahead. For instance, and we're still kind of doing random stuff. We can even skip 1,000,000 steps ahead. We're still doing random stuff. It's done this 1,000,000 steps. It knows. The Q values have stabilized in this setting. It knows what to do, but since we have this high epsilon value, we're not exploiting that knowledge. Right? So once we start to lower that epsilon value, we do a lot better.
So that's entirely because the probability is just making it choose something random versus prioritizing what it knows.
Exactly. And just to be clear, this is demonstrative. Epsilon of 80% is giant and probably way too high for real problems. But anyway, we lower this epsilon down to 0, and it uses the policy that it spent that time learning, and now it's able to kind of load them up. Yes?
So what would like lowering alpha do in this situation? Because that's like the learning rate, right? That's like how it's picking up this information?
Yes. So alpha is telling us, given some experience, how are we updating our Q values? Right? So this is a different concept. Here we're trying to converge on the Q values. The epsilon is choosing the actions for us, right? So alpha here is basically telling us how much we want to weight recent experiences that are based on our current estimation of the Q values. And epsilon is telling us how much we want to remove randomly to kind of explore state action pairs, parts of the state action pair space that we haven't seen yet. So definitely related in some ways, but they're different values. You want to vary them differently. Is that distinction clear? That's an important one. Great. Okay. So there's another solution, and that's we're going to have something called an exploration function. So the idea here is that in random actions, we're kind of exploring some fixed amount. But that's not really it's not really a great idea necessarily. Because if we can say, hey, there are these regions that I haven't seen, or that I've only seen once or twice, we can say, actually, it's valuable to go explore those regions explicitly, right? With this notion of this epsilon greedy search, we're just randomly moving through the space, so eventually we'll get there with some probability. But we know, if we haven't seen that we should probably go there soon. Right? Does that make sense? We want to learn these things early so that we can have as much time with a good policy to actually achieve our goal as possible. Right? So the idea here is that we want to explore areas where we don't know yet what's going to happen, and then eventually we stop exploring. And so we're going to use something called exploration functions to do so. So the idea here is that we're going to take our notion of Q values and we're going to kind of augment it with this sense of how many times we visited that state action pair in the past. So if we have this function here, this is giving us some estimate, or it's taking some estimate of our utility and some count of the times we've seen a specific event, a state action pair specifically. Then we have the estimate of the value plus some constant factor that we set divided by the number of times we've seen it. And so intuitively, what does this do? If we have only seen something, okay, let's make it n plus 1. So if we've only seen this 0 times and k is large, then the second term over here dominates this function, right? But as n grows bigger, what happens? That second term vanishes, right? It gets smaller and smaller and smaller with larger n, and the true value of the utility u that you're learning dominates, right? So this is just some way to express this concept mathematically, that we want to stop exploring spaces we've seen once we've already seen them a sufficient number of times. And this will allow us to bias our kind of exploration of the space to regions that we haven't seen very often yet. Does that make sense? Okay, so putting this into the math that we've seen so far, the idea here is that we're going to take, this is our regular Q update, right? This is what we've seen in the past with Q-Learning. This is just shorthand for this alpha blending that we saw, the running average with alpha, right? So this is our sample where we saw the reward plus our discount factor over the max of the things that we can do from there. Right? This is our regular Bellman equations for Q values, right? We're going to change it. And we're going to have this notion of adding this function in, where this is the value, and now this is the number of times we've seen that thing down in the future. Does this make sense? This has one really interesting implication, and it's coming from the same kind of behavior that was counterintuitive that we saw in regular Q-Learning. And do you remember last time when we had this notion that we were kind of going down the grid and we were falling off the fire pit, but we kept propagating these positive values backwards, right? Because we knew that from those states, because we'd seen that almost end state a bunch of times and had good experiences from there, even if we had a bad experience this time, we were learning that getting to that state was good, right? And so it was propagating these positive values, positive Q values backwards. This has a similar effect in that if you have some region that's highly unexplored, that highly unexplored space is going to influence these values further back, even through nodes that you've been through a bunch of times. So kind of intuitively what that looks like is that, you know, if you have some hallway and you left this space relatively unexplored, even if you go down this a bunch of times, this notion of this is an unexplored region is going to propagate backwards, and it's going to have you keep exploring down that hallway. because the influence of this unexplored region is propagated backwards, even through spaces that you've explored, if that's how you get to the unexplored region. Does that make sense? It's kind of a counterintuitive result here, but it's really powerful. Okay, so let's look at this crawler working, but now with an exploitation function. So it's kind of randomly exploring the space, it's learning how things work, it's biasing itself toward state action pairs that it hasn't seen before. But now it's moving. Right, we saw it take 1 million iterations last week to start moving. This is a very, very powerful concept.
This is because epsilon stays low?
No, this is excluding epsilon, ignore epsilon. This is taking that notion of how frequently have we seen things in the past and moving toward things that we haven't seen until we've seen them sufficiently, and then using that to do our notion of exploration. Right, so this concept is replacing this notion of epsilon greedy search. Yes?
So there's that k value in the exploration function, and how do we know what's a good value for that k value?
You don't. I mean, that's the problem with all these. You have some set of hyperparameters that you have to set, and the behavior of your reinforcement learning algorithm is going to depend really strongly on you having set those in the right way, but you don't know what they are. And the right way to set those is probably going to depend on some specifics of your problem that you don't know in advance, things like this. So this is what makes this kind of problem hard. Yes?
When you're doing your research, do you research for the optimal set of hyperparameters, or do you just sort of guess them based on the problem itself?
So there's a lot of things you can do. And this is more a machine learning question than a reinforcement learning question specifically. This kind of applies all over. But you can do some search over your parameter space. You can say, I've got 6 parameters. I can discretize that, grid it up, and search it over. I can randomly search. Depends on how expensive one learning instance is. Right? So if we say, I'm going to run reinforcement learning on this problem and see at the end of some number of iterations or at some notion of convergence how good it is. Right? That's one instance of learning. Right? We can do that a bunch of times where the thing we're changing is these parameters. Right? So you can search over your parameter space. You can do that randomly. You can do that in some structured way. You can do that in some smart way. You can start using smarter optimization techniques for doing so. You can start to estimate gradients with respect to your parameter space. You could have another machine learning algorithm that's learning the right parameters for this machine learning algorithm, right? But how do you set those parameters? Then it's turtles all the way down, right? These are hard problems. The right answer depends. Frequently you do grad student descent, which is where you have a grad student just try a bunch of random stuff and figure out. That's one of my favorite optimization algorithms. The one I use the most in grad school.
Human optimization.
Very interesting questions. There's a lot of nuance and research that goes into even how do we determine how to set these parameters. So, good question. Okay, I want to cover one more concept, and then I'll give you guys a little break, and then we'll come back. So, there's this notion of regret. Who knows what regret means informally? We all do, right? We all. When we talked about the slot machine, we had said, it turns out that second slot machine wasn't very good, right? With low probability, we were getting winnings, so we should have stuck with the first one. I regret having ever explored that in the first place, right? Well, in reinforcement learning, we can formalize this concept of regret. And basically, this is coming from the fact that if you learn the optimal policy, you're still making mistakes along the way. And so now we can start looking at the difference between learning rates. How fast did you learn the right policy? Even if you end up with the same policy at the end of the day, how fast did you learn it? Because that allows you to exploit that policy earlier, right? And so this concept of regret is what we're going to use to formalize that idea. So the idea is that if we measure our total mistake cost in some way, and we can define that as the difference between our expected rewards, including the things we did suboptimally, and the optimal set of expected rewards, what's the difference? And so minimizing regret means that we're learning to be optimal. We're learning to learn optimally, right? So we have to learn how to learn. And so an example here is that random exploration and then using this notion of an exploration function, both of these end up in the limit with optimal solutions, but one of them did it quickly, right? Okay, so random exploration would have higher regret in that case. Okay, so let's take 5 minutes, and then when we come back, we'll start talking about approximate Q-Learning. This one?
Just our own questions.
Yeah. Not for everyone.
Are you actually confused about that? Like,
I'm a funny guy, okay? I'm working on a tutorial for my Netflix special. What's up with this airplane? Jerry Seinfeld knew what was going on with those pencils. There was a puffy jacket. He was just telling a joke that made people laugh. He learned an optimal policy. It turns out the policy involves a little bit of sarcasm, a little bit of absurdity.
oh, I'm gonna play jokes. robots that are very similar to like that
But man,
robot.
that was
But, yeah, it's like a robot or something. Or do you think that's too bad?
and that is, I guess like
I'll see if I can do it.
Yeah, for the past like year, I was trying to work on an AI that would like help us track for a custom track and trying to so I'm not like 100% like knowledgeable about it yet, but I would love to practice.
Okay, let's get started. Is everybody back? Does everybody have your buddies?
Yep.
Neighbors? Okay. Alright, approximate Q-Learning. So when we started talking about both MVPs and reinforcement learning, I mentioned a pretty substantially restrictive assumption. Does anybody remember what I said? It's kind of a vague question. Let's rephrase it. What are some of the problems associated with both MVPs as we've seen them and reinforcement learning? Yes?
They're not optimal.
Well, they can be optimal. Some of the algorithms we've talked about converge to optimal solutions, for instance. Yes?
The Bayes assumption might not be right. The Bayes?
You probably mean the Markov
Yeah.
assumption. But yeah, that's a good point. Maybe there's some notion of history dependence that you can't account for in your state space, right? You can very frequently augment your state space, make it higher dimensional, give it more features to account for what in one abstraction was history and now is not. It just depends on the state. For instance, we talked about this car where if you don't know its velocity, you can't really talk about where it's going in some next time step. But were you to keep track of your velocity, so in that case, you would need the previous states, right? So the Markovian property doesn't hold. But if you keep track of your velocity as part of your state, now it does, right? That's a good point. That's not what I'm going to talk about here in a second, but it's closely related in a way that I'll say once we kind of hear some ideas. Yes?
I'm guessing you're going to talk about the packet complexity. Is that?
In a sense, this is kind of influenced by that. So you first, and then, yeah.
You can't build in intuition or like knowledge about how the world works. You just kind of, have a bunch of states and see the stochastic probabilities. So you can't say, well, I'm not going to try that because I know that.
Very good point. Not what I was looking for, but also will be related. Let's do one more yes, and then I'll just
Okay, so based on this title of this slide, I'm gonna guess you're gonna say that our past examples have been learning on specific problems and aren't generalizable.
That's also related. Okay, so the big, just for the sake of time, we'll move on. The big problem that I'm referring to here is that we had to keep track explicitly of every state and every action that we can choose from every state, right? But with non-trivially sized state spaces, that can become difficult or prohibitive, right? So in Q-Learning, you have to have a value. It's this lookup table, right? You're constructing values in this lookup table. You have to have one for every state action pair. You have to store that in memory, in the computer, or on the cloud, somewhere, right? But let's talk about some relatively small problems. So we had, way early, we had this notion of the state space of some Pac-Man problem, right? So we have, let's say, like a 9x9 grid. I'm setting myself up for bad algebra here again. But we have a 9x9 grid, right? And Pac-Man can live in this 9x9 grid, right? And we have dots in each of these, right? Let's say there's no walls other than the walls at the boundaries, right? And we have 4 ghosts that also live in this 9x9 grid, right? Spooky ghosts, spooky ghosts. I'm an artist, you can tell. What's our state space look like here? Let's talk about it. All right, so Pac-Man can live anywhere in how many places? Okay, so yeah, 81. places. Let's say Pac-Man can be in a ghost, but then you die. So we don't have to subtract that, just to make it a little easier. Okay, Pac-Man can live in any of these 81 places, right? What about the ghosts?
Also 81.
They each can live in 81, right? There's 4 of them. There's the 4th one, right? So, right? For every place Pac-Man can be, the ghosts can be in any place.
Can they be in the same place?
Sure,
Okay.
just to simplify this for a second. Right? Okay, but we also want to eat these dots, and so the right action, given even an instance of where Pac-Man and the 4 ghosts are, is going to depend on where the dots are, right? Because you want to kind of move towards dots. You don't want to prioritize moving to places that don't have dots, things like this, right? You have to keep track of where the dots are. So how many possible settings of dots do we have?
81 factorial?
2 to the 81, right? Each of the 81 grids can either have a dot or not. For each of those, excluding the grids Pac-Man's in, just for a second to make it easier, there can be some setting of where Pac-Man is. For each of those, there's some setting of where the ghosts are. In all of these cases, you have to act differently. Right? Does anybody want to tell me what this number is? Somebody has their computer open. Yes.
Are we also thinking it's got big dots?
I'm sorry?
The big dots?
Oh, if we have big dots, it gets even worse, right?
And walls?
Walls.
All that.
Uh,
I think that actually
2 to
restricts
the
the-
81 is 2.417 times 10 to the 24th, so.
Okay, 10 to the 24th, that's big. I guess 2 to the 81's big too, I don't.
No, that's
Somewhere on the order of like 10 to the 33rd.
10 to the 33rd-ish?
Yeah.
You want to keep that in the hard drive? Probably not. Does this look like a big problem? I don't know, I can't conceptualize numbers that big.
Yeah, doesn't it get bigger if we're doing Q-learning, which means we're storing the Q states for each of those?
And multiply this stuff times 4.
Or possibly.
Yeah, if you have a very small action space, if you have a large action space, much worse. Right? So what do? Q-learning is not going to work. Right? We can't store all of these. We can't, even if we learn the optimal, even if we had the optimal values, we couldn't use it. Right? So what do? Yes?
Well, search trees were pretty fast when it came to like solving at least Pac-Man instances, so maybe we could give our AI some sort of like search tree and like say, hey, like try to follow this, but if anything bad happens, keep track of that.
That's an interesting idea. It's not where we're going, but I like it a lot. Definitely. Yes?
Do we start collapsing some states and saying these states are essentially the same?
Yeah, intuitively. But how do you say 2 states are the same? Let's move on. I think that we'll explore that option here in a minute and it might become more clear. Okay, so basic Q-learning has to keep a table around of all the Q values. Right? In realistic situations, there's no way that we can possibly learn about every single state. In fact, we may not even be able to hold every single state in memory. Right? So instead we're going to generalize. So we're going to learn something based on how states are similar under some definition of similarity. We're going to use this to kind of inform how we do our actions, right? So we learn from some small number of training states, then we generalize that experience to new similar situations. So this is very similar to what we were talking about a minute ago about transplant. Right? It's all over machine learning, all over the place. And we'll see it a bunch here, especially at the end of this semester. We're going to start talking more about machine learning in general. Okay. Actually, let's connect these. Okay, so let's talk about Pac-Man. Let's say that we discover through experience that this is a bad state to be in. Looks pretty bad, right? In naive Q-learning, we know nothing about this state. Right? Those look completely different. They're probably very far away from each other in this state space under some notion of distance. Right? We can't even say things that are close by look the same. But conceptually, These are very similar situations for Pac-Man and DM, right? But Q-Learning says 100% distinct. We have to learn each separately, right? Even worse, if we know this one on the left here, we don't even know anything about this state. This is like one of those spot the difference games. Okay, yeah. Unless there never was a dot that started there in the first place, but that's a good point. Potentially some states are not going to be reachable, but for now we're just talking about the abstraction of what states look or don't look similar to Q-Learning. So these look distinct 100%. To make it more realistic, we could say that this state looks no different than the one where this stop is gone instead, for instance. Then the concept's the same. Right? Obviously, we should try to do better, probably. Right? We as non-artificial intelligence can look at this and say, these are all very related. If we had seen this not work out a bunch of times, we'd probably know that this was a bad place to be. Right? So what do we do? Well, how do we know? What kind of information are we taking from these various settings of the world to make those intuitions? Yes?
Relative distance of adversaries or like threats, essentially.
Yeah, maybe we say, hey, we're really close to these ghosts. What a bummer that is. Yeah. Right? Yes?
Maybe the area Pac-Man can move in without running into a ghost.
Yeah, maybe Pac-Man's available, kind of reachable, some notion of reachable volume that doesn't cause instant death, right? Yeah. Maybe how restrictive the area Pac-Man's currently in. Right? We look at these as humans and we say, we kind of do some internal, very opaque calculation and we say, this is bad. Right? But we're kind of relying on these higher order features of the situation. Right? There's some feature that says Pac-Man is this distance from a ghost. There's some feature that says Pac-Man's cornered. Even if the ghosts are far away, there's nowhere for Pac-Man to go. Right? Yes?
So are we supposed to create like arbitrary or very specific states to keep track of instead of every possible state?
So we're not going to change the state space. What we're going to do is we're going to try to say, write down some of these features, and we're going to change what we're learning. So we're going to take a feature-based representation. So the idea here is that we're going to describe the value of a state. So the states are kind of the same, right? Where the dots are, where the ghosts are, where Pac-Man is. But we're going to describe the value of a state using some vector of features, which are just properties. And what we're going to do is we're going to say, in some instances, these features indicate some preferential choices of action. In other instances, they would indicate a different preferential set of actions. Right? These features are functions from states to real numbers, and they capture kind of this intuitive, important aspects of states. So all of the things we've said about Pac-Man here, we could encode some feature function, right, that takes as input a state and maps it to some value, right? Proximity to ghost would produce a negative value, that's bad, right? Proximity to dot might be high and good, the number of ghosts, where they are, 1 over your square distance, is Pac-Man in a tunnel, all of these things, right?
So how do you balance more complex states like this? Because I think the problem isn't necessarily that he's right next to the red ghost or right next to the blue ghost, but he can't escape, right? Like there's no number of moves if they're acting optimally that he can get out of.
Yeah, so you could encode that
Yeah.
in a feature, right? The feature is just a function, it doesn't have to be analytical.
Sure.
You could have to do computation to determine what features. You could do, this is like layering some concept, but do BFS from there.
Yeah.
Just say, what's the size of the space like a beach? Maybe that's a feature. That kind of gets to this notion of, can you escape the ghosts, right? As long as it's fast enough, because we're going to have to look at these very frequently. But, yeah, we kind of just encode these features. Yes?
So the features are something that we're going to have to choose specific to the problem that we're solving.
Yes. Yeah, so again, hard problems, capital H hard, right? So we're going to have to kind of engineer our intuition in the form of some heuristic choices into how we solve these problems. These features, that's one way that we're going to use it. You could learn them. Now we're starting to put turtles on top of turtles again, right? But for now, we'll just say that we're engineering them based on our intuition. Yes, but we're still going to learn how they work together. Yes?
So will these features help us determine which states to then explore, or will they determine us, like help us determine the value of key states, or will we be storing these features explicitly or not?
We're getting there.
Okay.
That'll become clear in a second. So, yeah, we can describe the value of some state. We can also describe a Q state with some notion of features, right? It's kind of up to us. So, we have some set of features. We as humans have said these are the things that should matter when making a decision about how to act in your environment. In Pac-Man, we say, Pac-Man, we as humans think you should care about where the ghosts are relative to you. You should care about where the dots are relative to you. You should care about the number of dots left. You should care about how far you can go without dying. You should care about all these things, right? All of them. And then we need to learn some way to kind of weight those features based on what we're observing. Well, no, not based on what we're observing, but in some way that allows us to apply these features across all instances. So we're going to use this notion of linear value functions. So the idea here is that we have some feature representation. We can write a Q function or a value function for any state just using a few weights. So any state. What we're trying to do is we're trying to define one function that gives us smart behavior from any state. Because we can't have a function that describes smart behavior from every state explicitly, right? Because that's just Q-learning. We already talked about why we can't do that necessarily in many problems. So we need to learn some function that says these are the ways that you relate these things in such a way that allows for good behavior. And so what we're going to do is we're going to learn these weights. So let's just look at the Q aspect for now. So we have some features, right? These take state and action pairs and produce some value, similar to how we did last time. So now instead of Pac-Man's distance to the ghost, it's now Pac-Man in state, whatever, having chosen action, whatever's distance to the ghost. Or next step's distance to the ghost, or something, right?
It's like a positive version of the heuristic instead of estimating cost, it's estimating value.
Or it could be estimating cost. I mean, you could say there are negative features, right? These values don't have to be, the weights don't have to be positive, so they can influence either way. And we're going to learn that. Okay, so the advantage here is that we're kind of summing up the entire experience of life as Pac-Man in a few very powerful numbers. But states might share features and be very, very different in values, and this isn't going to encode that information, right? So this is kind of almost to approximate Q-learning, but that approximate word is there for a reason, right? Okay, here we are. So now we're going to substitute our Q value lookup table with this function, right? And so now the Q value of a state action pair is defined by some linear combination with varying weights of these feature functions that are arbitrary that we've defined based on our kind of intuition. Does this make sense? Okay. So in the past, we had this notion that we're going to observe some transition, right? We're going to look at the difference between what we had expected the value to be and what we got out of that experience, right? And then we're going to constantly be updating our Q value entry in the table based on what it used to be, plus some correction factor based on what we actually experienced. Well, based on the difference between what we experienced and what we expected, right? So this is just a different formulation of that 1 minus alpha plus alpha update, right? We saw both of these last time. approximate Q world, what we're going to be updating are these weights based on our experience. So the idea here is that if we have some weight, right? We're learning these weights as we go. We have some current understanding of these weights. Then these are influencing our decisions, right? And so the idea here is that we're going to say this notion of what we expected versus what we experienced being different is going to penalize our weights differently based on how strong they were. So the idea here is that weights that are large in magnitude are going to be penalized larger than weights that were small. And the intuition here is that if you imagine a weight being like how much a feature matters, then you want to say this good experience I just had or bad experience I just had is a function of the things that I thought at the time mattered, right? So I need to penalize, if I had a bad experience, the factors that were causing me to expect to have a good experience in that instance and allow me to choose that. And I need to support the ones that were providing good decision-making value. Right? This is kind of an abstract concept, but does that make sense? Okay. So the idea here is that we're adjusting the weight of the active features. This is another way to say what I just said, but maybe better. If something unexpectedly bad happens, we blame the features that were highly active when we made that decision, right? And so that means that in the future we're going to choose to avoid states that had high values for those features, right? So if we started out saying, hey, we have a positive weight distance from ghost, and so currently we're just running at the ghosts. Then as we experience bad things, we would say, hey, let's cut that down. Let's add some negative value, because that's the difference to that scale by some learning factor. Because we don't want it to be jumping around too much based on random samples from our environment, right? Yes?
Is that the same alpha as before, or a different one?
It is, yes, it's the same alpha as before in that it's this notion of how much do we weight recent experiences versus past experiences. Strategies for changing it over time might be different in approximate Q-Learning than in explicit Q-Learning, but conceptually it's doing something very similar. Okay. So let's look at, I only have a couple minutes left, so we're going to finish this next time, but first, let's look at how Pac-Man might behave if we were doing approximate Q-Learning with some combination of those features that we already talked about in class. In a few seconds when it starts. At some point I'll figure out how to scroll through videos on the iPad and then we can jump ahead. How is everybody? I promise it starts when. There we go. Alright, so we are watching literally every instance of learning this Pac-Man's doing. So there's not learning happening behind the scenes. This is every single experience Pac-Man's experiencing, and it's learning. This is the third iteration of Pac-Man running in this world.
So it doesn't seem like there's a weight associated with collecting the larger dots.
Yeah, I don't think this is considering the large dots in the feature space right now. In fact, I believe what this is doing is just encoding the distance to the nearest dot and the distance to the ghosts.
These ghosts random.
These ghosts are moving randomly. Yeah, similar to the rules that we've seen in the past. Oh, come on. Yeah, so I believe that they move straight until they reach a decision point and then randomly decide what to do at that point. But either way, this Pac-Man won the third game at play. Right? I'm sorry?
You didn't do badly either.
Yeah, I mean, that probably is playing Pac-Man better than I could. And the reason it's able to learn so quickly is because it's got this small set of features, distance to dot, distance from ghosts, that actually, were you to know the right way to allow those things to influence your decisions, pretty well describe a good way to play Pac-Man. If you're trying to go to states that move you closer to dots but further from ghosts with some weighting, that's what's happening. And it turns out it doesn't actually take very long to learn which of those things should influence you in a positive way and which of those things should influence you in a negative way. So we saw Q-Learning take on problems that are probably smaller in the state size than this, millions of iterations. And this learned to do it in 3. So this can be very powerful, but it comes with its own restrictions. So we'll talk more about this in the next class.